This presentation describes how to generate or create characterized resources while a simulation is running. It is common to have systems where resources arrive from the external world according to some random process. Then they stay in the system and follow certain operations. And then at the end of those operations, they leave the system and return back to the outside world. In this case, a simulation model of the system needs to generate resources arriving to the system while the simulation is running. In this presentation, we shall consider 4 different ways to generate resources while the simulation is going on. The first 2 models consider characterized resources, where the resources that belong to the same subtype follow their own separate inter-arrival process. The last 2 models describe the arrival of resources of the same type, where all arriving resources follow the same inter-arrival process, and the subtype of each arriving resource is determined probabilistically after the resource arrives to the system. The first model considers characterized resources of the same subtype that arrive to the system using their own separate inter-arrival processes. This approach will be illustrated by example. We shall consider a system where we are interested in the arrival of airplanes of different models. We define a car type called plane, where the first property I is an index, the second property Eng is the number of engines, and then that is followed by several other properties from property 3 to property 8. The exact nature of those properties is not important in this model. We then define 7 subtypes of the characterized type plane. The name of each subtype tells us the model of the particular airplane involved. The first subtype has the name B707. B707 has the index number 1 and has 4 engines. The second subtype has the name B727. This plane has the index number 2 and has 3 engines. In this manner, we defined additional subtypes such as B737, B747, DC8, DC9, and DC10. After that, we define another characterized type called an arrival scheduler. An arrival scheduler has 2 properties, I and A. I is an index, and A is the expected inter-arrival time for each subtype. After that, we define 7 subtypes, each of which corresponds to a particular subtype of the type plane. The name of the subtypes tell us the model of the airplane to which they apply. For example, the first one has the name AS-B707. AS stands for Arrival Scheduler, and B707 is the model number of the airplane to which it applies. The important thing is that there is a correspondence between the index I for the Arrival Scheduler and the index I for the plane subtype. In this case, they both have the index equal to 1. Similarly, the second subtype has the name ASB727 and has an index number 2 to match the index number of the plane subtype B727. After that comes the definition of 2 queues and 1 combi. The queue arrival schedulers contains the resources of the type arrival scheduler. The queue plane's weight contains resources of type plane, and the combi is called inter-arrival and represents the time between arrivals of planes of the same subtype. We then initialize the queue arrival schedulers with one resource of each subtype of the type arrival scheduler. As a result, at the start of simulation, the queue arrival schedulers will contain 7 resources, each of which will be of a different subtype. Because the queue arrival schedulers contains 7 resources, it will be possible for the combi activity interarrival to create 7 instances at simulation time 0. Each one of those instances will have a different duration. The duration of the combi activity interarrival follows an exponential distribution whose expected value is the property A of the arrival scheduler in the instance interarrival whose duration is being determined. Because each instance of interarrival will contain a different arrival scheduler, the property A of that arrival scheduler will be different, and as a result, the durations of the various instances of interarrival will be different. The last 7 statements are the statements that will actually generate resources while the simulation is running. Each one of these statements involves an action event, which is the same for all statements, and it is before end interarrival. Each statement also involves an action. The action is generate. The argument of the action generate is a number followed by a subtype of a characterized resource, for example, 1B707. Each of the before-end statements also includes the optional precon statement that determines the conditions under which the generate action will take place. For example, the first statement has a precon that compares the number 1 to the property I of the arrival scheduler that is in the current instance of interarrival. If the I property of the arrival scheduler equals 1, then the action will be taken and generate 1B707. Otherwise, no action will be taken. As a result, every time an instance of interarrival ends, 6 of the 7 before-end generate actions will do nothing, and only one of them will generate one plane of the appropriate subtype. The second model also considers a system where characterized resources of the same subtype arrive to the system using their own separate interarrival processes. This model uses the subtype approach, which does not require the use of precondition statements. The first statement defines the characterized type plane, which has several properties beginning with n, the number of engines, and is followed by property 3 to property 8. After that, we have the definition of 7 subtypes. Each one of those subtypes has a name, such as B707, followed by numbers that describe that subtype's properties. Notice that the properties of a plane in this case do not include the index I. Following this, we have the definition of the characterized type arrival scheduler. Arrival scheduler again has 2 properties. A is the expected interarrival time, and PL type is a property that will contain a number which is actually a pointer to the subtype of the plane that needs to be created. This introduces a very important concept. The name of each plane subtype, such as B707, is actually a variable that serves as a pointer to that subtype. Because B707 is a pointer, it can be used as a value of the property of another characterized type, in this case of an arrival scheduler. For example, the subtype ASB707 has two properties. The first is 8.1, which is the expected interarrival time, and the second one is B707. That B707 is actually the pointer to the subtype of the airplane that needs to be created. After that come the same definitions for the queue's arrival schedulers and plane's weight and the combi interarrival. The initialization of the queue arrival schedulers is the same as before. That is, we initialize arrival schedulers with one resource of each subtype of arrival schedulers. For example, one ASB707, one ASB727, and so on. In the end, arrival schedulers will contain 7 resources, all of a different subtype of arrival scheduler. The duration of the combi interarrival is again exponential, with an expected interarrival time given by the property A of the arrival scheduler that is in the current instance of interarrival. The last statement is the most important statement because it is the statement that actually generates planes of the appropriate subtype. This statement occurs at action event before end interarrival, like in the previous model. The action is generate, again like in the previous model, but this time generate does not have a precondition. It generates one resource of a particular subtype, and that subtype is given by the PL type property of the arrival scheduler in the current instance of interarrival. For example, if the current instance of interarrival contains an arrival scheduler ASB707, then the PL type or plane type of that arrival scheduler is B707. So the arguments to the generate statement is a number followed by a subtype. Generate in this case is followed by the number 1 and the subtype B707. As a result, it will create one plane of subtype B707. Clearly, this model uses less statements than the previous model. There is only one before-end statement and does not require any preconditions. However, implementing this particular model requires that one understands that the subtypes of a characterized type are actually pointers to that subtype and can be used as arguments to the generate statement. The next two models represent a situation where characterized resources arrive to the system using the same interarrival process, so there is only one interarrival process. When a resource arrives to the system, its subtype is determined upon arrival based on random sampling. We shall again illustrate this approach by using as an example the arrival of airplanes to the system. In this case, we have 3 types of airplanes: heavy airplanes, medium airplanes, and light airplanes. All types of airplanes arrive to the system using the same interarrival process, which is represented by the combi arrival. There can only be one instance of arrival at any given point in time. This is accomplished by using a semaphore, as explained later. As a result, when one instance of combi arrival ends, another one begins. Every time an instance of combi arrival ends, we shall generate one plane, which will then be routed to the queue a plane weight. That plane will then be taken by the combi sort by type that will release the plane to one of the succeeding queues. In this example, the probability that a plane is of a particular subtype, heavy, medium, or light, is 1/3. Moreover, we shall assume that each arriving plane needs to know the type of the plane that follows it. The first approach that we will describe here is an indexed approach that uses precondition. The first statement defines the characterized type A-plane, which has several properties. The first property is type, followed by property 2, 3, and 4. After that come the definition of the three subtypes, A heavy, A medium, and A light, each of which has a different type number, 0, 1, and 2. Notice that each plane subtype is identified twice, first through its subtype name, for example, A heavy, and then through its type, for example, 0. After that comes a safe prop for the type A plane called next type. This safe prop will allow each plane to know the type of the plane that follows it. We then have the definition of the nodes for the network shown in the figure. The variable choose_next_type has an expression that does random sampling and returns the value 0 or 1 or 2 with probability 1/3. The save value next_A_type is initialized with the result of the variable choose_next_type. The semaphore for the combi arrival is a logical expression that prevents arrival from having more than one instance at any given point in time. The duration of the combi arrival is exponential with a mean inter-arrival time of 1. Next come three before end statements, all of which are defined for the combi arrival. For each instance of the combi arrival, only one of these before end statements will actually perform an action. This is determined by the precon statement, which compares a next_A_type to a number such as a 0, 1, or 2. If, for example, the current value of the save value next_A_type is 0, then because the precondition next_A_type equals 0 will be true, the action generate will create one A-heavy airplane before end of the arrival instance. The A-plane generated in this manner will then be released through link AP1. The statement on release AP1 will assign to the save value next_A_type the result of the variable choose_next_type. The next statement also occurs on release through link AP1 and will assign to next type the result of next_A_type. Notice that next type is a safe prop of the plane that is currently inside the link AP1, whereas next_A_type is the name of a save value. This way, each plane which is released through link AP1 knows the type of the plane that will be generated after it. It is stored inside its safe prop next type, and it is represented by the number 0, 1, or 2. Each generated A-plane enters the queue A-plane wait, which allows the combi sort by type to start. Sort by type takes the arriving A-plane and then determines where to release it based on the release where statements for the outgoing links. Each of the outgoing links AP3, AP4, and AP5 has its own release where statement. For example, release where AP3 has the logical expression type equal to 0. In other words, link AP3 only allows resources whose type equals 0 to flow through the link. If the A-plane inside the instance of sort by type has the type equal to 1, then link AP3 will not allow that plane to flow through. However, link AP4 will allow that plane to flow through and be delivered to the queue, medium queue. The last model also considers a system where characterized resources arrive to the system using one inter-arrival process, and their subtype is determined upon arrival based on random sampling. This model uses the subtype approach, which does not require the use of a precondition statement. The first statement defines the characterized type, a plane, which has the property SType followed by three more properties. The SType property holds a pointer to its own subtype. After that come the statements for the three subtypes, A heavy, A medium, and A light. Notice that the SType property for each one of these subtypes is indeed a pointer to its own subtype. So the value of SType for the subtype A heavy is also A heavy. The first A heavy names the subtype. The second A heavy is a pointer to the subtype itself. The property SType is needed to route the resources after the completion of combi sort by type. Each A-plane has one save prop called a next type, which will be used to store the type of the airplane that follows this particular plane. After that, we have the definition of the various nodes of the network. The variable choose_next_subtype does random sampling and returns one of the three subtypes, A heavy, A medium, A light, with probability 1/3. The save value next A type is initialized with the result of the variable choose_next_subtype. Notice that the save value next A type in this case contains a pointer to a subtype of the characterized type A plane. The semaphore for combi arrival ensures that arrival can only have one instance going on at any given point in time. The duration of the combi arrival is exponential with a mean time of 1. The next statement generates or creates the arriving plane based on its subtype. It occurs before end of combi arrival, and the action is to generate one next A type, where next A type is the save value that contains a pointer to the subtype of the plane that will be created. Thus, only one statement is needed to generate the correct subtype of plane to be created. The next statement chooses the subtype of the plane that will arrive next some type later. It occurs again before end of the combi arrival, and it assigns to the save value next A type the result of the variable choose_next_subtype. When the newly generated plane flows through link AP1, we assign to its save prop next type the current value of the save value next A type, which is a pointer to the type of the airplane that follows. The last statement shows how the links AP3, AP4, and AP5 filter the resources that can flow through them. For example, release where AP3 has the logical expression that compares S type to the subtype A heavy. Thus, only if a plane has an S type equal to A heavy, it will be allowed to flow through link AP3. A similar release where statement must be defined for each one of the links AP3, AP4, and AP5 so that each arriving airplane in the sort by type combi will only be allowed to flow through one of the outgoing links and be deposited in the appropriate queue. An interesting question is, why do we have to define the property SType? The property SType is used only to filter the planes by subtype. It is necessary for the simple reason that Stroboscope does not have a built-in variable that can return a pointer to the subtype of a characterized resource. If such a variable existed, and for example it was called a subtype, then the release where statement would have the logical expression subtype equal a heavy, and there would be no need for the property SType. Unfortunately, there is no built-in variable that returns the subtype of a particular characterized resource. These four models are good examples that can be used as template to model the arrival of characterized resources to a system.